Hey everyone, and welcome back to part 5 of this series where we cover an entire machine learning project. And today is all about feature engineering. And more specifically, we're going to filter subtle noise, so not outliers. That we covered that in the last video, but now we're going to filter subtle noise. We're going to identify parts of the data that explain most of the variance through principal component analysis. And then we're going to add numerical, temporal, frequency, and cluster features. So this episode will be packed with methods to add features to your machine learning data to potentially, hopefully, improve our predictive modeling. As usual, this document that you're seeing right now will be linked in the description, so go check that out. Also, if you're new here, make sure to check out the playlist over here that is linked in the document. And this will link to the full playlist with all the episodes that we're covering in this project. So we're going to build upon the data sets that we have built in the previous episodes. So if you want to follow along completely, make sure to check out also those previous episodes. If you just want to learn about the feature engineering techniques, then you can just continue to watch this episode. Okay, let's get into it. And to get everyone on the same page, let's start with a quick definition or description of what feature engineering is. So this is the process of transforming the raw data into more or extra meaningful relevant features that we can use for our machine learning models. So we're basically going to look at each of the features that are currently present in our data, and we are going to try and come up with ways to manipulate them, combine them, etc. in a way that creates new features and potentially more information that we can provide to our model. So here is a brief description of what I've just explained, and we will cover most of the examples shown over here. So this episode will be packed with different methods, and I will probably split this up into 2 episodes because it might get too long. But anyway, let's continue right now to the Python files that we will be using. And as usual, you can click on the arrow over here and download the Python files. So there are 3 in total this time. So the build features is the empty script that we will be building in. So this contains all the sections for everything that we will be doing. And I've also added 2 additional Python files over here with some functions that we are going to use. And these functions are taken from this GitHub repository over here. And that is the machine learning for the quantified self repository. And in this episode, we will be using functions from this repository over here, mainly from chapter 3, the data transformation.py file, and from chapter 4, the temporal abstraction.py file. So those are the files that you are seeing right here. I've made small adjustments to them, but you can open up the files over here. You can see where they're from and that I've made some small adjustments on today actually. And you can go ahead and download these files or copy and paste all of this Python code and paste it into a file, but make sure, as usual, that they are in the correct folder. So today we are going to work from the source folder and in there the features folder. And in there you should have the build features file. So as you can see, this is empty right now. And you're also going to put the data transformation.py and the temporal abstraction.py file in here. And in doing so, we can import the classes that are defined files, so the low pass filter, principal component analysis, and also the numerical abstraction class. We can import them with the following import statements. So we are basically creating our own classes, Python packages like this that we can import into this file and start using. And coming back to our document for today, we've briefly covered what feature engineering is. And now the next step is to deal with missing values, which we are going to do through imputation. So in the previous episode, we have removed some outliers and replaced these values with nans. So basically now there are gaps within our data set, and most algorithms cannot properly deal with missing values. So we have to come up with a way in order to tackle those. So let's get into it, and we'll start off as usual by loading the data frame. And for this, we'll create a data frame variable, and we'll call the pd.read, sorry, not CSV, pickle method. And then as usual, we'll link to our data folder. We'll go to the interim files, and then we're going to continue with our O2 outliers removed Chauvenet's.pickle file. And let's start up an interactive Python session. And also this is a critical point to make sure that you can import the classes from the files over here. So this should run without any errors, but only if you have placed these files in the features folder, and also make sure that the naming is correct. So everything should be like this, and then you should be able to import it without any errors. So for me, it succeeded, and now we can continue by reading the data frame as usual and have a look at it. So this is the exact data frame that we exported in the last episode, and that is because we are using a pickle file, which is very convenient. So we can continue. Now, just like in the last episode, we're also going to define the predictor. And that is because we will be referring to these quite often. And the predictor columns are all the acceleration and gyroscope data. So for this, we're going to call df, and then we'll call columns. So this will show us all the columns in the data frame. But then we're going to create a subset up until the 6th column, which is, as you can see, up until the last gyroscope value. And we're also going to convert this to a Python list to store it here in the predictor columns variable. Next, I'm going to import the plot settings. So I just copy and paste these, so you can just type these over and run them as well. So we're going to be using the 538 style again, and we'll make sure that our images are nice and big. All right, now we're ready to deal with the missing values. So if we have a look at our data frame and call the .info method, we can see that there are 9,009 entries in total. And here in the overview, we can see for each of the columns how many missing values there are. Or basically, we can see how many non-null values there are. And this also tells us how many missing values there are, of course. If we are looking at the predictor columns over here, we can see that basically all of them are missing some of the values. And that is the result of our outlier detection methods that we applied in the previous episode. So now let's deal with these missing values. And for this, I'm going to give a few examples of what we're actually going to do. So I'm first going to create a subset of the data frame, and I'm going to select a subset and set it equal to a specific set. And I'm just doing this at random over here. So let's see, set 35. What are we looking at? We're looking at a heavy row. So let's, for example, take which one has a lot of missing values. So let's take the gyroscope Y value and plot an image for this. All right, and now you can't see it in here, but let's just pretend that, and let me switch to the whiteboard over here and make it a bit larger. Let's pretend that there are missing values within this set. So for example, let me just take a pen and illustrate it like this. So for example, do it like this, and then here, this, so, and then another one, and then also it misses this peak. So let's pretend this is the actual data, and we're missing some values over here, here, and here, because the outlier detection model, the points that are circled over here as outliers. So for example, what could have happened is there was a point over here that dropped all the way down, and then went below a certain threshold, and then the model would say, okay, this point is definitely an outlier. So then it would introduce a gap over here. Same thing over here, but then, for example, like this. So it would cut off. You get what I'm saying. So there are gaps within the data. And now there are several ways that we can deal with these gaps in the data. And the first one is that we can, for example, drop the rows where there are many missing values. So we can look at the whole data set and we can just say any row where there is a gap, missing value, we just drop the row. And now, of course, this would result in less data. So this is not always the best or preferred method, but when there's enough data, it's a solid option. But you can also look at imputation. And this basically means that we're going to look at the gap and we're going to impute a different value over here. And to come up with that value, we can look at different statistical properties of the data, for example. So we can look at the mean, the median, the min, the max, stuff like that. But we can also try and interpolate the data, meaning that we're trying to connect the last point over here and the next point over here. So try and fill in that gap. And that is what makes the most sense in this situation, at least in my opinion. So that is what we will be applying. So we're going to interpolate the data, meaning that anywhere where there is a gap, a missing value, we're just going to connect the dots over here and interpolate them linearly. So we're just going to create a straight line, and most of the times it will just be one value that is missing. So it will just interpolate one value. So do it like this, and here also like this. So that is what makes the most sense to me in this situation. So let's see how we can do that in Pandas. So let's get rid of this and also this. And Pandas has a nice function method that we can use out of the box in order to do this. And that is the interpolate function. So we can take any column basically and call, so for example, like this, and call the interpolate. And this will interpolate the data linearly, just like in the example I've shown you. And now all we have to do is loop over all the predictor columns for which we want to interpolate the data in order to store the results. So we're going to create a for loop. So for column in predictor columns, and then we're going to jump over here, and then we say the data frame, and then we refer to the column. We're going to override that with the data frame column, but then interpolate it. Let's run this, see if it works. And now let's have a look at the data frame and then call .info. And now we should see that all of the predictor columns shouldn't contain any missing values. So here you can see that there are no missing values anymore. So job's done for this part. Okay, so the next thing we're going to focus on is calculating the average duration of a set. And this is a preparation that we have to make in order to later apply the Butterworth low pass filter, which is a filter to basically filter subtle noise in the data set. And let's start off by giving you an illustration of what we want to accomplish with this filter. And for that, I'm first going to create a subset by selecting an individual set again. So I'm just going to take a random set 25, which is a heavy overhead press. And then let's look at the Y acceleration and let's create a plot. So what we can see over here is a movement for 5 repetitions. So remember, the data is split up in heavy and medium sets. Heavy sets were 5 repetitions, medium sets were 10 repetitions. And here we can see that there are clearly 5 peaks, so 1, 2, 3, 4, 5, which translate to the 5 repetitions in this heavy set. And as you can see, these lines are pretty jagged, they're pretty sharp. And we can take a look at another example. So let's just take 50, for example. Oh yeah, this is a nice example because this is a medium set. So this is a bench press medium. And what we basically want to accomplish with the low pass filter is we want to filter out subtle noise within the exercises. So we can clearly see the movement patterns of the individual repetitions over here. So we start off on the low end and then we accelerate to a higher point and then we come back down again. And the same for the bench press. We can see the clear patterns that are repeating over and over again corresponding to the different repetitions. By applying the low pass filter, we can basically make these lines smoother, meaning that we are just going to look at the overall movement pattern and not necessarily at like these small tiny differences that are apparent between every repetition and also every participant. So like the small incremental adjustments of the bar and your hands and feet position, for example, that can come up during a rep, during a set. We want to filter out that and look at the big movement patterns. And that's why we have to know how long a repetition takes, because in doing so, we can later adjust the frequency settings and basically attune to a frequency that is higher, meaning faster repetitions itself, in order to filter out the noise. And this is quite complex and is probably still a bit abstract right now. So let's just get into it and then I will demonstrate it with an example. Okay, so let's just first calculate the average duration of a set. And we can do this by taking a subset, and let's just look at set 1, which is a heavy squat. And then let's have a look at the index and take the starting. So this is a timestamp. So this is the timestamp on which the set started. And what we can then do is we can take this and then put it in front and then say, let's have a look at the final timestamp. So by doing the -1 in the index over here, we select the last index from this data frame, from this subset. And here we have 2 timestamps. And if you subtract 2 timestamps, you get a time delta variable. So we can do this. Let's have a look. So we have a time delta and it says you have 20 seconds and 400 milliseconds. So this is the difference between the last and the first timestamp, meaning this was the duration. And now we can also take that duration and on a time delta variable, we can also call seconds. And then we can see that it's 20 seconds. So this will round it to the nearest second. So this is how we can calculate the duration for a single set. Now let's do that in a loop to calculate the average duration. And for this, we're going to loop over all the unique sets that are present in the data set. So that will be S in data frame, and then we call the set column, and then we call unique. So let's have a quick look at what that's like. That is just a set of all the unique sets. And then we're going to define the start and the stop. So let me just copy and paste this, put this over here, and then say start equals, and make sure to replace the 1 with S from the loop. So also make sure to spell start correctly. So we're going to loop over all the sets, and then we're going to select start and stop. Then we're going to calculate the duration, which is stop minus start, which results in the time delta. And now we're going to add this duration to the data frame in a new column, and also taking the set into account. So in order to do this, we're going to say we want the df.log, where, and then in parentheses, the set column equals the S. So this is the selection. And then we're going to select a new column. So this will be duration, and we're going to set that equal to duration. And then let's just round it to seconds, just like we did over here. Let's run this and see what we get. So we now have our new data frame, which has a duration column. So here we can see set 64 took 16 seconds to complete. And now we can use this new duration column to take the data frame and basically group by, and then group by category, and then only look at the duration column and then take the average. So now we can see that the average duration of heavy sets is 14 seconds and the average duration of medium sets is 24. Bring this even further, we can say duration df equals the group by function that we've just did. And now we can take a look at the first element in here. So that is the duration, average duration for the heavy sets. Take a look at the second element in here. That is the duration, average duration for the medium sets. And then we're going to divide that by the amount of repetitions that was present during heavy and medium. So 5 and likewise 10. And now if we take a look at this, we can see that for the heavy sets, the average duration of a single repetition was about 3 seconds. And for a medium set, which is lighter, of course, and therefore easier to perform, the average duration was 2.5 seconds for a repetition. All right, awesome. We could have also just looked at the plots itself and did like a visual inspection of how long it took, but now we can back this up with data and we know exactly how long each repetition lasted. So this gives us some information that we can use in the low pass filter that we will look into now. Now, and just like the previous methods that we have applied, we're not going to dive into all the technical and mathematical details of the methods over here, because I want this to be a very practical course, practical tutorial that you can follow along. But of course, it's also important to understand the underlying principles. So I suggest if you want to learn more about the Butterworth low-pass filter, you can look that up on your own. There is some information over here in the document, so you can check this out in the resources. So you can find a brief description here and also a visual representation of what different frequencies look like. But for now, let's continue by defining the parameters that we need. So we are going to leverage the class from the data transformations.py file. But before we get started, let's just create a copy of the data frame that we will be using to apply the low-pass filter to. So let's define df low-pass, which will be an exact copy, and then continue by defining an instance of the low-pass filter class. So we are going to create a class instance of the low-pass filter class called low-pass, and then let's just run this. So what this does in the background is we have first loaded this class variable over here, and we have now initiated an object called low-pass, which has access to this function over here, so the low-pass filter. And if we look at this low-pass filter over here and then look at the function that is in here, we can see all the required parameters. It includes a data table, which is the data frame, then also the column that we want to apply the filter to. We need a sampling frequency and a cutoff frequency. So table and column are pretty straightforward. These are new variables. And this is also why we have calculated the average duration of a repetition. The sampling frequency, in our case, is the step size between the individual records within our data frame. And as you remember from part 2, we have set this to 200 milliseconds, meaning 5 instances per second. So that is what we have to fill in as the sampling frequency. And then the cutoff frequency is the frequency that we want to set our filter to. And basically we have to play around with this setting, look at the results that the filter is giving us, so a visual inspection, and also considering the average repetition duration that we calculated. So this is a value we will be playing around with, and I will show you some examples in a bit. Okay, so let's start off by defining the sampling frequency and the cutoff frequency. And first one we'll define as fs, and we have to specify it like this. So this will result in 5, meaning that there are 5 instances per second. So we take this in milliseconds, 1 second, and when we divide it by the differences between the records. So remember, between each of these records, there is a step size of 200 milliseconds, resulting in 5 instances per second. So that is where that is coming from. And then for the cutoff frequency, we're going to start with 1. And now let's start off by applying the filter to a single value. So we're going to continue with df low-pass, and we're going to take the low-pass class instance that we've initiated over here, and we're going to call the low-pass filter function. So remember, low-pass filter class contains the low-pass filter function like this. And in here, we have to put the self, which is not relevant right now, and we need the data table and the column. So let's first start off by inserting the low-pass data frame, and then let's start off as usual by looking at the Y acceleration. And then what else we need? We need the sampling frequency and the cutoff frequency. We're going to input the fs, and we're also going to input the cutoff. Make sure we run this, and then we can also have a look at the order. That defaults to 5, so we can leave that at 5 for now. And let's see what we get. So we can run this and have a look at the new data frame, and we can see that there is a new column over here, acceleration Y, with the low-pass filter applied. Now, let's have a look at what we have actually done by applying the filter, by comparing this new column with the original column. And for this, I'm going to copy and paste a piece of code in here. And this is all just some data visualization stuff that takes a long time to type, but this is not a data visualization episode. So I'll just go ahead and first select a subset again. So you can just type this over as well to follow along. We select set 45 in this case. This is just random, but we're looking at a participant E doing a medium deadlift, and then we can check this out. So this is a deadlift. And now what we can do is we take that data frame and we're going to, or the subset, better to say, we're going to plot the original data, so the raw data, and the data with the filter applied. And we can already tell that the filter has done its job in smoothing the data. So hopefully now you get a better understanding of what this filter is used for, because before this was quite abstract, but here we can clearly see, okay, we have the original raw jagged lines over here. And here we can see by applying the filter, it even got rid of the 2 peaks that we see over here. And now this brings us to the question, what is the right cutoff frequency to use? So let me give you an example by setting this cutoff frequency higher, so to 2, for example. And this is kind of counterintuitive, but by setting the frequency higher, we allow higher frequencies, meaning more jagged and rough lines, because they are faster at the higher frequency movements. Meaning, to sum up, the higher this number, the more or the less we filter smooth the data. So high number, close to raw data, low number, smooth data. So let me show you what that looks like by just running this piece of code again. So here you're looking at cutoff frequency 1. Now we change that to 2. And we can see that the data now looks a lot more like the raw data. It's not the same. We can definitely tell that some smoothing is applied, but not so much anymore. And now let's say if we set this to a half, and now this results in very smooth lines, and is probably too much if we consider the problem at hand and trying to create a model to identify the different exercises. We are now in the position where we have to figure out what the best cutoff frequency is. And this is best done by, first of all, looking at the graphs over here, then considering the duration of the exercises and trying to find a nice balance between smooth lines without the subtle noise, but still seeing the apparent characteristic patterns for each of the individual exercises. And to speed this process up, I'm going to cut straight to the point, and that is a cutoff frequency of 1.3. That is the value that I used in the original paper. And let's have a look at what that looks like. So here we can see that there are still some peaks and valleys in here, but it is overall much smoother than the original data frame. And we can even tweak it, for example, a little bit and see, okay, what does it look like if we set it to 1.2? There's not much difference for this set over here. So probably setting it to 1.2, 1.3 doesn't matter that much, but I'm gonna set it to 1.3 to leave even more variation in the data. And also, this will also be a feature that we could potentially experiment with later down the line. So once we have our prediction pipeline ready, we can see what the effect of changing the cutoff frequency has on the predictive performance of our models. So just like outlier detection, feature engineering, and also this particular parameter in particular, you have to tweak and test and run experiments in order to find the best value. And now the next step is to apply this filter to all of the columns, which we will be doing in a loop. So we're going to loop over column in all of the predictor columns, and we will say low pass, they have low pass. And then we're going to this over here and say, we're going to change this up with the column that we're looping over. And now this will add the low pass filter to the data frame in a new column. But in this case, we actually want to override the original values. So This is something that you could consider. So you could add the smooth as additional columns and then later compare them, or you can override the original columns. And what we are going to do right now is we're going to override the original columns. So in order to do that, we have to first take the data frame and then apply the filter. So a new column is added. And then we're going to basically override the column that we've just created. So this will be column, but then plus and then underscore Lopez. And then finally, we will delete the additional column. So what this will do, loop over all the predictive columns, apply the Lopez filter, then override the new column with the original column, and then it will delete this column. So that's what we are going to do. So let me make sure that our Lopez df is clean again, so it doesn't have any of the filters applied. And then we're going to loop over everything. Instant, beautiful. All right, so now all of our values are updated and overwritten. Great. And then it's time to move on to principal component analysis, PCA for short, which is another very interesting technique. And the mathematical foundation for this is also pretty complex, just like the Butterworth low-pass filter. You can find some additional information about principal component analysis in the resource over here. But basically, to summarize, it's a technique used in machine learning to reduce the complexity of data by transforming the data into a new set of variables called principal components. Basically, this transformation is done in such a way that the new set of variables captures the most amount of information from the original set while reducing the number of variables necessary. So to summarize, we can look at a set of variables. So for example, all the acceleration and the gyroscope data, and then try to combine them in such a way that we can reduce them to 1, 2, or 3 columns while still being able to capture or explain most of the variance. And this helps to reduce the complexity of the data, makes it easier to analyze and make predictions. So here is a brilliant video explaining step-by-step in depth of how principal component analysis works. But for our example, we're just going to continue by applying it and then see what it looks like. All right, and to get started, we're going to look at the principal component analysis class over here in the data transformations.py. And we can see that there are 3 functions in here. So we have a function to normalize the data, which is necessary in order to calculate the principal components. And also we can determine the principal component explained variance. And we will use this in order to determine the total amount of principal components that we would like to use. So the optimal number, which we'll get into in a bit. And then eventually we have the apply PCA function. So if you want to understand how this works on a more theoretical level, you can have a look at the functions over here and then also look up more information about how PCA works. But for now, let's just continue by creating a new instance of the class principal component analysis, just like we did for the low-pass filter. So we're going to define a new object and we're going to set that equal to the class. So now we have a new class instance. And before we continue, let's just also create a new df PCA, and we're going to set this equal to the df low pass and then copy it again. So we can always come back to this line of over here and reset our data frame. So now the first step is to determine the optimal amount of principal components. And like we've just mentioned, we are going to do that with the function over here, determine PC explained variance. And that takes as an input a data table and the columns that we want to implement. So that will be the predictor columns over here. So there's also a comment over here, perform PCA on the selected columns and return the explained variance. So let's just first take a look at what this will result in. And then I'm going to explain how we can use these results to determine the right amount of principal components. So we can start off by calling PCA and then call the determine PC explained variance. And then we can put in the df PCA and also the predictor columns. So we're going to apply the principal component to the first 6 columns of this data frame. And now we can store that in a value called PC, and let's run this. Now this will result in a list of 6 values over here. And that is because there are 6 columns in total that we introduced. And of course, PCA is a dimensionality reduction method. So we want to move from a lot of variables, a lot of columns, to less columns. So we want to explore a total amount of principal components up to the total amount of columns that we're introducing. And choosing 6 in this case wouldn't make much sense, because then we haven't actually achieved anything, because we would still end up with 6 columns. And now the next step, so we have these values over here, and we are now going to look at a method to determine the optimal amount of principal components. And we can do this by using the elbow technique. And for this, I'm going to switch to the document again over here. And this is a technique you also often see when doing k-means clustering, for example, to determine the optimal amount for, or the optimal number of k. And here there is a brief description about how this works, but basically the optimal component number is chosen as a number of components that capture the most variance while also not incorporating too many components. So we want to find an optimum over here. And this is done by plotting the variance captured, the array we just calculated, against the component number, and then selecting the point at which the rate of change in variance diminishes, which is called the elbow. And before explaining this further, let me first just illustrate how this works. So I'm going to copy and paste a piece of code over here that basically plots these values that we just calculated on a square graph. Okay, so now what we can see over here on the y-axis, we have the explained variance. And then on the x-axis, we have the principal component number. And this is a perfect example of an elbow that we see around the number 3. Meaning that as we increase the principal component number, the explained variance decreases, but after a certain point, after 3 in this example, there is a diminishing effect. So coming back to the explanation over here, this is done by plotting the variance captured against the component numbers and then selecting the point at which the rate of change in variance diminishes. So it's about rate of change in variance. As I've said, this is a perfect example of how we can illustrate that and how this is called the elbow technique. So in this scenario, it's quite straightforward that 3 is the optimal number for our principal components. So let's now continue and implement that. So let's have a look at the apply PCA function. Apply PCA given the number of components we have selected. We add new PCA columns. So we include the data table, the columns, and the number of components. So pretty straightforward. So let's see how that works in practice. So we'll start off by the PCA data frame again, and then we'll set that to PCA, and then we say apply PCA, and then we provide the data frame, the predictor columns, and then the number of components, which is 3 in our example. Let's run that and let's have a look. So we now have a data frame, and then if we scroll all the way to the back, we can see that we now have 3 components over here. We have basically summarized these 6 columns into the 3 principal components over here, while capturing or explaining as much of the variance as possible. We will leave the principal components in here next to like all the other columns. So not like the low pass filter, we're not going to override the initial values, but for now we're going to just keep them in here, and later doing feature selection, we're going to check whether the principal components actually perform better than the individual columns. But for now, the last thing that we have to do in here is visualize them to get a better understanding of what we've just done. And for this, I'm going to create a subset again. So let me just copy and paste this over here and now change up the data frame. And let's say we're going to look at set 35. So what we got a heavy row. Perfect. And now let's look at this subset and then a selection based on only the PCA columns. So that would be PCA1. And then let's just copy paste this once more, 2. So we got a selection of only the principal components, and then and here we can see the result of our principal components for this particular set. And that concludes the principal component analysis for now. So we can have a look at the data frame. You have the original values with the low pass filter applied, and then 3 additional columns created by the principal component analysis. All right, so then we can move on to the next set of features. And I can't say this enough, but the math behind the PCA and the low pass filter is quite complex, and I really encourage you to look it up and learn more about it if you want to apply it in like your own projects. But I just want to show you like how it works, and later when we're going to look at predictive modeling, it all comes back together and we can see how each of the features is performing, and then we can also make better decisions. But that's why I'm briefly going over this. Normally this would require a much more thorough study into the actual results of the principal component analysis to validate whether they are actually useful. All right, let's continue with the sum of squares attribute. And for this, I'm going to refer to the resources again. And here is a part from the original report that explains how the sum of squares is calculated. Basically, so to further exploit the data, the scalar magnitudes called R of the accelerometer and gyroscope data were calculated. R is the scalar magnitude of 3 combined data points, so the X, Y, and Z. And the advantage of using R versus any particular data direction is that it is impartial to device orientation and can handle dynamic reorientation. R is calculated by basically taking the squares of all the original vectors and then taking the square root again to basically bring it back to a single positive scalar. So let's do that in pandas, and we're going to start off by defining the acceleration R, which is equal to let's copy the data frame again. So we'll take the PCA data frame and we call this df squared equals. Okay, so we set it equal to the PCA data frame, and then from the df squared we're going to first look at the acceleration. So we'll take the x and then we'll square it like this in Python, and then we're going to plus this, and we're going to do that 2 more times. So x, y, and z of acceleration, and we square it. So coming back to the formula, this is the part under the square root. Now we're going to do the exact same for the gyroscope data. So we're going to select AC in this case, hit Command D or Control D 3 times, I guess. 1, 2, 3, yes. And then we type in gyroscope, and now we do the same for the gyroscope data. So let's do that, and this will result in a single series combining all of the 3 results. And now the final step is to take the df, create a new column called acceleration R, and we're going to take the acceleration R that we created, but now let's take the square root and then do that one more time. Select acceleration, hit Command D, type in gyroscope, check that out as well. So we can first have a look at the values over here and then take a look at the square root. All right, looking good. So now final step is to visualize that again. So let's take another subset, do the same trick. By now we know the deal. Let's take number 18 for now. What we got? Medium row. We also got a row in the previous one. I want another one. Squad, medium, perfect. So we have the subset, and what we can now do is we can have a look at the subset and then create another subset actually of the gyroscope R, accelerometer R, and gyroscope R. So we get that, and then let's just call the plot method and then also say subplots equals true. So we get 2 images over here, and is that looking correct? Yeah, I think so. All right, so now what we can see over here, so we have now combined the acceleration and the gyroscope data into scalars using the formula over here. And we will later explore how this could potentially impact our models, but the main goal of implementing a magnitude scaled version of all the values over here is because it is impartial to the device orientation. And this could help us to make the model generalize better to different participants. So let's have a look at the data frame again. And we can see that we have 5 additional features as well as the filtered version of the columns over here, of course. And that also concludes this video for now, because as you can see, we still have quite a lot of topics to cover, and otherwise this video will get too long. So I will stop this right here and then continue in the next one. If you've been following along, please like this video and subscribe to the channel, and then I'll see you in the next one.